Hi, Questers! Today's quest begins with something you feel every single day, but likely misunderstand fundamentally. It isn't an asteroid, or a war, or even pollution. It is simply heat. But this isn't the heat of a summer day. It is a fundamental shift in the energy architecture of our planet. Earth isn't collapsing from a sudden explosion. It is collapsing from a fever, slow, quiet, and relentless. If you are ready to understand the physics, the chemistry, and the brutal mathematics of what is actually happening to our Earth, subscribe and join the quest, because this story affects every single breath you will take for the rest of your life. Let's start by dismantling the biggest misunderstanding about global warming. The problem is not that the sun has become hotter. Solar irradiance, the amount of energy the sun throws at us, has remarkably stable over the last few decades. The sun is innocent. The problem is entirely about how Earth handles that energy once it arrives. To understand this, we have to look at the physics of light. The sun gives Earth energy in the form of short waves of light. This is visible light and ultraviolet energy. It travels through our atmosphere with ease because oxygen and nitrogen, which make up 99% of our air, are transparent to these short wavelengths. The energy hits the surface, warms the rocks, the oceans, and the forests. But here is the trick. Earth doesn't stay hot forever. It tries to cool itself by releasing that energy back into space. Earth does not give the energy back as visible light. It changes it into heat and releases it as long-wave infrared radiation. For millions of years, this system worked perfectly. The heat rose up, slipped through a specific atmospheric window, and escaped into the cold vacuum of space. But that opening is now being closed. This is where the invisible villains enter the story: greenhouse gases. But let's get specific. It's not just gas. It is a matter of molecular geometry. Carbon dioxide, or CO2, is the primary architect of this disaster. A CO2 molecule consists of one carbon atom flanked by two oxygen atoms. This structure allows it to vibrate in a very specific way. When infrared radiation traveling at a wavelength of 15 microns tries to leave Earth, it hits a CO2 molecule. Because of that specific 15-micron wavelength, the CO2 molecule absorbs the energy, vibrates, and then re-emits it, not out to space, but in a random direction. Often, that direction is right back down at us. We have pumped so much CO2 into the air that we have effectively thickened the glass of the greenhouse. In the pre-industrial era, the atmosphere contained about 280 parts per million of CO2. Today, we are pushing past 422 parts per million. We haven't seen concentrations this high in over 3 million years. But CO2 is just the heavy lifter. Methane is the sprinter. Methane, or CH4, is released from leaking gas pipes, rotting landfills, and agriculture. Molecule for molecule, methane is far more dangerous. Over a 20-year period, a single molecule of methane traps over 80 times more heat than a molecule of CO2. It absorbs radiation at different wavelengths, 3.5 and 8 microns. It is plugging the few remaining holes in our thermal blanket. Then there is nitrous oxide, N2O, from fertilizers and industrial chemicals. It is nearly 300 times more potent than CO2 and stays in the atmosphere for over a century. The result of this chemical soup is not just warming. It is a measurable breakdown in Earth's thermal efficiency. We can measure this using a metric called Earth's energy imbalance. Right now, our planet is absorbing more energy than it is releasing. The imbalance is roughly 1.6 watts for every square meter of the Earth's surface. That sounds like a tiny light bulb, doesn't it? But you have to multiply that by 510 trillion square meters of the Earth's surface. When you do the math, the numbers become terrifying. The amount of excess heat we are trapping is equivalent to detonating 5 Hiroshima-sized atomic bombs every single second. Not per year, per second. That is the thermal load we are placing on the planetary system, 24 hours a day, 365 days a year. So, if we are trapping that much heat, why aren't we burning up instantly? Why isn't the air temperature 100 degrees? The answer lies in the ocean. The ocean is the only reason civilization has survived this long. Water has a tremendous specific heat capacity, meaning it takes a huge amount of energy to raise the temperature of water by even 1 degree. Here is the most underreported statistic in climate science. Over 90% of the excess heat trapped by greenhouse gases has not gone into the atmosphere. It has been absorbed by the oceans. The top 2,000 meters of the ocean are warming at a rate that is frankly hard to comprehend. In 2023 alone, the ocean absorbed approximately 15 zetajoules of heat energy. To put that in perspective, the entire global economy, every car, every factory, every light bulb on Earth, uses about half a zettajoule of energy a year. The ocean absorbed 30 times the total energy consumption of humanity in just 1 year. We are treating the ocean like a battery, charging it with thermal energy. But batteries eventually discharge. This heat is not disappearing, it is changing the physics of the water itself. First, there is thermal expansion. As water warms, it expands. About 40% of the sea level rise we observe today isn't from melting ice, it is simply the water getting bigger because it is hotter. Second, this heat is killing the chemistry of life. Warmer water holds less oxygen. We are seeing deoxygenation zones expanding in the tropics, where the water is becoming too breathless to support complex life. We are literally suffocating the ocean. But the ocean can only hide the heat for so long. Eventually, that heat interacts with the ice, and that is where the feedback loops begin. Ice is the planet's shield. It acts as a giant mirror. Fresh snow and thick ice have an albedo, or reflectivity, of about 0.9. This means they bounce 90% of the sun's energy straight back into space. It is a free cooling system. But as heat melts the ice, it reveals the dark ocean or land beneath. Dark ocean water has an albedo of about 0.06. It absorbs 94% of the solar energy. This creates a vicious, self-sustaining cycle. The heat melts the ice. The loss of ice increases absorption. The increased absorption creates more heat, which melts more ice. We are seeing this play out in real time. Arctic summer sea ice has declined by nearly 40% since 1980. We are moving toward a blue ocean event, where the North Pole is ice-free in summer. Once that white shield is gone, the Arctic stops acting as a cooling system and starts acting as a heater. This brings us to the most dangerous concept in all of climate science: tipping points. A tipping point is a threshold where a system changes its state irreversibly. Think of it like pushing a boulder up a hill. You have to push hard, but if you stop, it rolls back. But once you push it over the peak, it rolls down the other side on its own. You can't stop it anymore. We are currently flirting with several catastrophic tipping points. The first is the permafrost. In the frozen grounds of Siberia, Canada, and Alaska, there is a frozen layer of soil that has been locked away for millennia. This permafrost contains dead organic matter, ancient plants and animals. It holds an estimated 1,400 billion tons of carbon. That is nearly double the amount of carbon currently in the entire atmosphere. As the Arctic warms, which it is doing 4 times faster than the rest of the planet, this soil thaws. Microbes wake up and start eating that organic matter. They release the byproduct, methane. If we trigger a rapid thaw of the permafrost, it could release a carbon bomb that no amount of human emission cuts could counter. We would lose control of the thermostat. The second tipping point is the Amazon rainforest. We call it the lungs of the earth, but it's also a sweat gland. The trees cycle water, creating their own rain. But as we cut down the forest and heat up the region, the trees are dying. Scientists warn that if we lose just 20–25% of the Amazon, the hydrological cycle will break. The rainforest will collapse and turn into a dry savanna. Instead of absorbing carbon, the dying forest will release billions of tons of it. We are dangerously close to this edge, with roughly 17% already deforested. The third, and perhaps most terrifying, is the slowdown of the AMOC, the Atlantic Meridional Overturning Circulation. This is the great ocean conveyor belt that brings warm water north and sends cold water south. It regulates weather for billions of people. Fresh water from melting Greenland ice is diluting the salty ocean water, making it lighter and preventing it from sinking. This stalls the engine. Recent data suggests this current is at its weakest point in 1,000 years. If it collapses, which some models suggest could happen as early as the 2050s, it would freeze Europe, dry out the monsoons in India and West Africa, and cause sea levels on the US East Coast to jump. It would be global climate chaos. But let's bring this down from planetary physics to the human body, because you are a machine that needs to cool down too. Humans are heat engines. We run at roughly 37 degrees Celsius. To survive, we must shed the heat we generate. We do this primarily through sweating. But sweating only works if the air is dry enough to accept the moisture. This is where the wet bulb temperature becomes critical. Wet bulb temperature is a combined measure of heat and humidity. When the wet bulb temperature hits 35 degrees Celsius, which equates to 35 degrees Celsius at 100% humidity, or roughly 46 degrees Celsius at 50% humidity, the laws of thermodynamics take over. At this threshold, the air can no longer accept your sweat. Your body loses the ability to cool itself effectively. It doesn't matter how much water you drink. It doesn't matter if you are sitting in the shade. If you are outside in these conditions, your internal temperature will rise. Your proteins will begin to denature, literally cooking like an egg white. Your organs will swell. Death follows within hours. We used to think these conditions would only happen in the distant future. We were wrong. Parts of the Persian Gulf, Pakistan, and India have already briefly touched these lethal limits. We are now seeing heat waves that are not just uncomfortable, but theoretically unsurvivable for humans without air conditioning. And this heat is expensive. The economy is not immune to physics. When it gets too hot, labor productivity collapses, construction stops, agriculture yields plummet, rails buckle, power grids fail. The data is stark. In 2022, heat waves in Europe wiped out an estimated 0.3% to 0.5% of the continent's GDP. By 2050, the World Bank estimates that extreme heat could cost cities in Europe and Central Asia up to 2.5% of their annual GDP. In hotter regions like Southeast Asia and India, the loss could be far higher. We are looking at a future of climate apartheid, where the wealthy pay for cooling and the poor suffer the consequences. The International Labor Organization projects that by 2030, heat stress could destroy the equivalent of 80 million full-time jobs globally. That is an economic catastrophe masquerading as weather. History offers us a warning. This is not the first time Earth has had a fever. 56 million years ago, there was an event called the PETM, the Paleocene-Eocene Thermal Maximum. Massive amounts of carbon were released into the atmosphere, likely from volcanoes or methane hydrates. Temperatures spiked by 5 to 8 degrees Celsius. The oceans became acidic. Many species went extinct. But here is the terrifying difference. During the PETM, that carbon was released over thousands of years. The rate of release was roughly 1.7 billion tons of carbon per year. Today, human civilization is releasing carbon at a rate of over 10 billion tons per year. We are changing the atmospheric chemistry 10 times faster than the most extreme natural warming event in the last 66 million years. Nature had thousands of years to adapt to the PETM. We are giving our ecosystems and ourselves only decades. The speed is the killer. Ecosystems can migrate if the climate changes over a millennium. They cannot migrate if it changes over a mortgage cycle. So, where does this leave us? We are standing at a fork in the road, and the physics doesn't care which path we choose. Path 1 is business as usual. We keep burning fossil fuels. We breach 2.5 degrees Celsius or 3 degrees Celsius of warming by 2100. In this scenario, we cross the tipping points. The Amazon dies. The permafrost melts. Portions of the Earth become uninhabitable. Hundreds of millions of people are displaced. It is a world of permanent crisis. Path 2 is rapid decarbonization. We slash emissions. We electrify everything. We stop deforestation. We invest in technologies to pull carbon out of the air. In this scenario, we might stabilize at 1.5 degrees C or 1.8 degrees C. It will still be a bumpy ride. We will still lose coral reefs. We will still see sea levels rise. but we avoid the collapse of civilization. We keep the fever survivable. This is the final truth of today's quest. The planet is not fragile. Earth has survived asteroid impacts that boiled the oceans. Earth has survived being a ball of ice. The planet will be fine. It will recover. It will evolve new life. It just might take a few million years. Civilization, however, is fragile. Our agriculture, our borders, our cities, our economies, they all rely on a stable climate that no longer exists. Heat is the silent killer because it doesn't destroy by force. It destroys by changing the base rules of reality. It changes the chemistry of the air, the physics of the water, and the biology of our bodies. A planet doesn't need to burn to become unlivable. It only needs to be slightly too hot for slightly too long. The thermostat is still rising, but for the first time in 4.5 billion years, the species causing the fever knows exactly what it is doing. We have the data. We have the technology. The only variable left is the will to act. If this deep dive changed how you see the world, if the data resonated with you, hit like and share this video. Share it not just to help the channel, but because this information needs to be common knowledge. And subscribe to Quest Hut, because our next quest is even harder. See you, Questers!